Well, hey there, HVAC pros and enthusiasts. Are you ready to take your skills to the next level? The HVACR Learning Network has just launched an exciting new e-learning course, High Performance Heat Pumps. And guess what? We're giving you free access to the first 2 chapters. Whether you're in the field, training for that next step, or simply want to sharpen your expertise, this course is packed with everything you need to understand and master high-performance heat pump systems, especially inverter-driven cold climate heat pumps. And the best part? You can access it anytime, anywhere, right from your favorite mobile device. It's HVACR learning made flexible and convenient for you. So what are you waiting for? Click the link. Dive into the HVACR Learning Network and start your free trial today. Your journey to HVACR mastery begins here.
At Service Logic, we believe the future of the skilled trades lies in training and development. And that's why we created the Edge, a platform dedicated to empowering our greatest assets, our people. From hands-on training to leadership development, Edge is where technicians grow their skills, expand their opportunities, and build lasting careers. Because when people succeed, our companies, our customers, and our industry thrive. This is the Edge. This is the future of the skilled trades.
I chose iConnect training equipment because I already previously had some iConnect training equipment. And I was very pleased with the equipment I had, the quality of it, and pre-designed labs that came with it. So when I expanded it more into their catalog, I decided I wanted to get this refrigeration trainer in my program to expand my program. My experience so far using the TU-155 has been pretty good experience, especially my second year students, and the light bulb kind of syndrome goes off when you see that little flicker in their eye and they're, oh, I got it. That's what us instructors, what we look for is the I got it moment. And this helps me to the I got it moment with my students, and that's what's my goal to achieve.
We are Daikin, the #1 global indoor comfort provider. Our innovative home and building solutions are engineered with energy efficiency and sustainability at their core, ensuring improved indoor air quality for all. From heating and cooling to ventilation, air purification, refrigeration technologies, and connected devices, we're at the forefront of technology, addressing the pressing challenges of sustainability.
Well, hello everyone. Thank you so much for joining us on Did You Know, the ESCO HVAC show. Hey, Sharp Sonny. We are grateful that you're joining us, right? We do this for you. Todd Kler is joining us. Todd, what's going on, bro?
Hey, how we doing?
Joining us from sunny California. How's the weather out there today, by the way?
Almost 100 degrees today, 99.
That's pretty crazy. It's like
Yeah.
73, 72 or so here in the Midwest. So, Sharp Sonny, where are you joining us from, right? This is for you, right? You know, we are blessed to be able to provide this show to give back to the industry. You know, our mission here at ESCO is to provide everyone in the industry with the resources to be successful. Whether you're a student, you're an educator, you're a technician, whether you're a business owner, we are here for you. Yeah, Eugene Todd is joining us today. Eugene, I know I will be looking for your critique on this because we are going to nerd out so bad today, and I got to
A
make
little
sure
bit.
that everything is correct. This is like a preview for the class that I'll be doing at our conference. Milwaukee, fantastic. Hey, what's the weather like up there too, by the way? And I've
In the
not seen you on the show before. So if you've not been on the show before, Sharp Sunny, we always like to know where everyone's joining from. This is a community that is continuing to grow and develop. We always have people from all over the world. So it's interesting to see where everyone's joining from. No, don't be quiet, Professor Silberstein. We're going to be looking for you. 84 in Denver. That is pretty warm, isn't it,
Wow,
Howard?
that's warm, Howard.
Yeah, that's not good for the snow. He won't be doing any of that anytime soon. Maybe up in the very, very peaks where it gets, like.
Yeah.
All right. So those of you who may not know Todd's been on the show quite a bit in the past. It's been a little while. Kendrick, thanks for joining up in Chicago. And Todd and I were talking about, doing some more of this co-hosting, bringing in, some additional co-host from the community. And so there's a lot of educators out there. You want to join me sometime? Let's pick a topic and let's
Yeah.
do this. Todd is actually going to be here in a couple of weeks. The week after our conference, I'm going to be taking off for the week. I've got a bunch of remodeling that I'm going to be doing at a house that we're closing on. So I'm going to take the week off, and Todd and Dirk Nauman is going to be joining. They're going to be running the show for that week. Jocelyn will be here with them, kind of helping keep things on track. And, what we do is we try to pick different topics, and Todd and I, man, we think a lot alike. Wouldn't you agree?
You'll see. Yeah.
Sharp Sunny, that's awesome. Fantastic book. Depends on which one. He's only got, like a whole shelf
Yeah,
and
which one?
slew of them out there. Actually, just updated. So at our conference, we're going to be releasing some new books. Be on the lookout for a new version of one from Professor Silberstein. Really
Yeah.
excited about that one. Okay. Are we ready?
Yeah, let's do it. Let's go nerd
This
out.
is deep. This is okay. So for those of you who if any of you were at the class that I did last year at the National HVACR Education Conference, I went down a pretty steep rabbit hole learning about refrigerants and where they came from, how we get different molecules, right? Okay, so for this year, I wanted to go deeper and talk about where do they actually come from? How do we create them? Now, we're going to go down so far. Yeah, we're going to start on the periodic table. We're going to talk about some naturals, which I'm really struggling to even call naturals now. And oh yeah, you're definitely going to need that thinking cap today because I've got some things that I'm going to be asking of you. It's probably going to take us all out of our comfort zone just a little bit. Scott, glad that you're joining us again. He's over in Ohio. Oh, Eugene, he's giving it away.
Uh-oh.
So
He
this
did.
is the 20th anniversary of the National HVACR Education Conference. And this is going to be the 20th year for Pressure Enthalpy Without Tears, with a newly revised version covering a lot of our new refrigerant characteristics. Okay, are we ready?
Yeah, let's do it.
Okay, this is a lot. And so if we get too far ahead, if you're not following along with where we are, let us know in the chat. Remember, we are here for you, so we want to make sure we're answering any questions that you might have. Now, this is it's a component, it's a piece of the class that I'll be doing this year at the conference. And we'll just show you. We'll show you where we're going with this.
Clown around. And I was really disappointed that Clifton, you didn't show up in your class.
I know. I'm gonna have to move a wardrobe over here into the studio, so I got everything we need. But don't worry, we got props. Like I said, Todd and I think so much alike. We started putting some of these presentations together. We were sharing some ideas, and right before the show, we were getting ready to do things, and Todd shows up with the props, and I'm like, all right, he's on it.
A few.
So the question is, where do refrigerants come from? Well, it really helps us understand that they are all engineered gases. And by the time we get to the end of this show, you're probably even going to question the word natural refrigerants. So be thinking about that as we're moving forward. All right. So Todd, you've got it in your background.
I do.
besides, well, even CO2, really.
Yeah.
Almost every refrigerant that we know is constructed of components, all coming off from our periodic table. So at the core of all of our refrigerants, we have a carbon base, right, Todd?
Yeah. I don't have a. Do I have another black one?
Well, I know you got
Oh,
some others. Depending
yeah.
on what refrigerant we're going to build, we're going to surround that with additional refrigerants,
Yeah.
additional components like hydrogen, chlorine, fluorine. And today we're even going to discuss,
Here's some carbon.
there we go, when we start introducing some oxygen into the mix.
Yeah.
And so we've done a few classes. If you look at the refrigerants across the bottom, those are different compositions of refrigerants. We've got blends, we've got olefins, which we're going to talk about today with some hydrocarbons and other variations. But it all comes down to understanding where they come from so that we understand how they function.
And
Like,
how
why
how
are
they're
some
made.
refrigerant, huh?
And how they're made.
Yeah, exactly. Because how they're made will help determine like how flammable they are, how toxic they are, what applications they work well in. Why is one inexpensive, one's very expensive? It could be different in different locations around the country and around the world. And it really is intriguing. And Lowell, you're exactly right. Um, our industry is progressing at lightning speed, and we are all right. I'm going to get some slack for this statement, Todd.
Yeah, maybe.
A2L refrigerants are a transitional refrigerant.
Oh, they're not here to stay. It's a bridge. It's a total bridge to what? Natural.
Others,
Yeah,
what we've
or
been
others.
calling natural. So, Lowell, what you're going to see is you're going to see changes in equipment. You're going to see changes in refrigerant. Pretty much everything that you're comfortable with right now will be gone in the next decade. And so we're going to be working with a lot of other refrigerants, but what are they, right? And why do they act the way they do? So, at the foundation of many of the refrigerants that we currently work with, right, we start with a methane molecule. And there's others. We'll show
Yep.
you others, other variations. So, when people say, well, how much propane is in this new refrigerant? Well, if you really want to go there, almost every one of our refrigerants started with some type of a hydrocarbon, but was chemically modified along the way. Howard, that's right. Everything's in transition. It's in constant evolution. ESCO is like the epitome of transition. They've been here to help educators in an industry move through so many different transitions. If it wasn't for the National HVACR Education Conference, I went there in 2019 for my first time. If it wasn't for that conference, I would have never went down the path that I have been on for these last 7 years because things were changing. My company sent me to that conference and I went, oh my gosh, this all makes sense now. And that's really what we do here is we all join forces to discuss these transitions and try to repaint them with crayons so that it makes sense for all of us, right?
Yes.
All right, Todd. So we're going to start with two foundational gases
But where do they come from?
and where they come from. So let's talk about methane as one. We're going to bounce a little bit in this conversation. So we're going to talk about methane and all different variations of it. And we're going to talk about carbon dioxide. Okay?
Yeah.
Because there's some really interesting things with carbon dioxide. CO2 is becoming a very popular refrigerant, not just in commercial refrigeration, but in many applications.
Monoblocks.
Well, have you seen the Sanco CO2 water heater?
Yep.
It's a CO2 residential air to water system,
Yes, it
right?
is.
Residential. We're going to be seeing a lot of these products. So we just need to know, like, why are we using that? So we're going to talk about a couple different perspectives today. We're going to talk about methane and other hydrocarbon gases in their natural form, as well as their man-made synthetic form.
Mhm.
And we're going to talk about CO2 in the same way. Sound interesting? Okay.
Let's do it.
All right. So, Todd, West Coast, California, you got ocean, right? The ocean produces some methane.
Yes, it does.
It's all
so do the
chemical
dairies.
processes. Hmm?
So do the dairies.
We're almost there.
Yeah.
So it's all about chemical reactions. It's all about using enzymes. It's all about breaking down chemicals to form other chemicals. Methane is one that comes from a natural chemical reaction. Oh, it, it is so deep.
Very deep.
It just, I can't hardly fathom how deep this is. Oh
Dad
my
joke.
gosh. Where's my sound effects? I got to fire up my sound effects soon.
Yeah, you do.
All right. So one of our sources of a natural methane, not the only sources though, Todd.
It's not.
One that really intrigued me. And I've heard my teenage stepdaughters joke about this before, but they take it very serious. They take it very serious about the amount of methane that's being produced by our commercially developed food, right?
Yes.
Around the world. It actually is quite a bit. So if we think about cattle in particular, goats run through the same process. They bring in food, they bring in oxygen, they bring in H2O, and they have a variety of different enzymes and other components like fungi and protozoa and bacteria in their digestive system that can break down those foods, those starches, the H2Os, the O's, can break them down and actually form methane gas. A3, highly flammable gas, right? Comes out both sides, Todd.
Yes, it does.
It's actual methane.
Yeah.
Didn't start from the ground as methane. It came from that process of that decomposition. Now, an individual cow can produce 150 to 250 pounds of methane per year. And their methane takes about 12 years to actually break down into its core components again. A lot more than what I would have thought of.
A lot more.
Do what?
A lot more than you would think.
Yeah, a whole lot more. Multiply that times a billion. That's 150 to 250 billion pounds around the globe. About 1 billion cattle is what they're estimating in the global commercial trade. Now, one form of methane that we encounter a lot is a natural form of methane, but it came from the same anaerobic processes, right? It came from the decomposition of materials that was affected by enzymes and other reactants that cause decomposition of proteins. We end up with a natural gas that gets locked into layers in different sedimentary layers. Okay, so this is a naturally formed gas.
Billions of years ago.
Billions of years. Now, to demonstrate how that actually gets sustained in the ground, we're actually witnessing a very interesting thing in the permafrost right now. This has just popped up in the last few years. We're actually seeing methane explosions out of Russia and in some of the northern parts of Canada, where we're witnessing permafrost releasing its methane gas, being ignited, and actually having small explosions. And we've even seen some. All right, I'm gonna hop over to the video. You wait till you see this. I can hang out with these chicks. Like, they're having a lot of fun, but watch what they're actually doing, right? All right, here we go.
Beneath the pristine ice here in Alaska, greenhouse gases simmer. This flame ignites methane gases that lie trapped in the permafrost or the soil that forms the Earth's frozen crust. Researchers say as permafrost is melting faster and faster, it's accelerating the release of greenhouse gases like methane and carbon dioxide. Dr. Vladimir Romanovsky heads the international program for monitoring temperature rise in permafrost.
Well, it's interesting you pull that video, but I think when I see that Clifton, I think of a frat house and lighting methane on fire.
Gosh, I got some good stories. I don't know if I can do them live, but boy, I've got really good methane stories sometime. My best friend Jerry West, I'll have to make sure he's on the show sometime if we ever have that story. Right?
But we can use your imagination.
Use your imaginations. All right. So natural methane, we're having releases of natural methane, but there's another process where we actually acquire methane. Now, this is the one where we have to think about, is it a natural process or not? Okay, ready? Hold on a second.
Crude oil is delivered to the refinery through various forms of transportation, such as pipelines, ships, trains, and even trucks, and is stored in large tanks at ambient temperatures, typically around 70 degrees Fahrenheit. From the storage tanks, crude oil is sent to a furnace for heating, where the temperature can range between 650 and 670 degrees Fahrenheit. The heated crude is then sent to a distillation tower, where the pressure inside the tower is typically in the range of atmospheric pressure. Once the crude oil begins to heat and vaporize, this mixture of hydrocarbons will travel up the distillation tower. And as the vapor travels up, it is cooled to the point where the individual fractions begin to condense out at what is known as the dew point of that fraction. These condensed fractions are then removed from the side drawers on the tower. The lightest portion of the crude leaves at the top of the tower as a vapor. These materials have a boiling point of less than 90 degrees and are typically comprised of components such as methane, ethane, propane, or butane. As you move down the tower to the fraction with a boiling point range between 90 and 220 degrees Fahrenheit, you get what is referred to as light virgin naphtha or light.
Okay, so when we start talking about the process of removing different types of gas out of crude oil, we're actually going to witness a variety of different gases that we utilize as refrigerants. Okay, so Todd, in this process, you and I were talking about, the different types of gases that come off from that vapor section, right? Those lower temperatures. So if we take a look at this, we're going to encounter a variety of gases that we're going to talk about, but there is an additional component of this that I didn't fully understand until you and I had this conversation.
Right.
Tell me a little bit about this other byproduct that comes out of the petroleum distillation.
From the refineries, yeah. So we all might know we used to use CO2 a lot, right? CO2 as a gas for condensation, blowing out traps,
Great,
whatever it might be.
blowing out drain lines.
Blowing off condenser coils if you can't run water because somebody's watching. You can't have the will go down the drain, right? A lot of different things we use CO2, compressed gas, right? But I have a kegerator, not necessarily for beer, but for beverages in general.
Yeah,
and
pressurizing beverages, sure, carbonating them.
And carbonate, exactly. And so when the other day, a couple weeks ago, it was back right around the holidays, my in-laws came out. They like to drink beer, and I had to go get some new CO2 refill, and I went and got the bill, and I'm like, and I like to support my local mom and pop shops, and I'm like, holy moly, what am I paying for? Well, that's because the refineries here in California, a lot of them have been shut down, and the process, therefore the CO2, less refineries, less CO2. But at that top level, where it's not listed on this diagram, is, if you haven't picked up on it yet, CO2.
CO2 comes off as a byproduct gas, and off from the combustion process. I'll show you here in another minute of how our scrubbers are actually working. So if we take that furnace that was being used to heat up that crude oil,
which leads me to another thing, Clifton, is this really truly as you mentioned, is that really truly a natural process? If we're man-making this fire,
rethink, right? We're taking a natural product, but we are intentionally separating it. And here in a minute, we're going to use heat and water and pressure to modify it, which to me becomes a synthetic process. It's a man-made process. Well, when we think about the scrubbing of that, when it says BF gas, that's the blast furnace that was being used to heat that crude. What we're going to do in some of these processes, we're going to add a scrubber to the exhaust of that. And we're going to run it through absorbent traps. We're going to manage the pressure of that. And we are going to capture compressed CO2 off from that blast furnace. So it makes sense. If we we always thought about California as, having oil refineries. But what's happened to oil refineries recently in California, Todd?
A lot of them have been shut down. Although recent weeks, maybe they'll start opening back up.
Right.
But
But it can make us realize that by shutting those refineries down, we actually were affecting the availability and the cost of
CO2,
CO2, compressed
which
CO2,
used to be cheap.
used to be cheap. Okay. Well, let's look at another perspective. Let's look at some of our natural forms of CO2. CO2 is a natural byproduct, right? We see that in photosynthesis. We see that in respiration of not just plants, but animals. We see it through anthropogenic, functions, through power plants, like through exhaust and, burning of fossil fuels.
Correct.
We see it in the ocean, as carbon is setting and decomposing. Another interesting one that I hadn't thought about is how much. We're talking like 13 to 15% of all of the CO2 released into the atmosphere actually comes from manufacturing of concrete. And I thought, okay, let's think about that for a minute. Let's think about that CO2. What's happening? Well, we're actually taking our cement products, we're running it through a furnace, heating it up to separate it, right? In that process of separating the lime out, not only are we burning fossil fuels, but we're also releasing carbon deposits. We're introducing oxygen. We're oxidizing the components of it. We're crushing the limestone, releasing it to the atmosphere. We're running through the clinkering process where we're superheating that with fuel once again. We got release of combustion and our processing plants. We have a lot of CO2 being released. That is now starting to get converted to capture that CO2 so that we can actually use that CO2 for commercial refrigeration applications. So another form of man-made CO2 that we are using for CO2 refrigerant. Okay. Got those thinking caps on, everybody?
Here we go.
All right. And I'm going to leave this one up for a minute. Where do you all think is the most common place that we get refrigerant grade CO2 from? So, boy, I need our
Yeah, except Jeopardy.
So in
What
the chat,
is?
let us know where you think the CO2 that we are using in our refrigeration systems and in our keggerators as well.
Yep.
Where do you think the majority of that comes from? It was not at all what I expected. I know there's a little bit of lag time in social media going into the chat. Hopefully we have some answers. Surely we have someone out there that
I'm sure
at
there
least
is.
has a thought. Well, I can tell you what my thought was.
Supply house. Okay, yeah, Eugene. Well,
that's where it all comes from, doesn't it?
Yeah.
Well, I always wondered, I guess I assumed that CO2 was something that was captured out of gases out of the atmosphere, something that we separated and that we filtered, and it was a natural gas. Until I learned what it actually does. Maybe it's because everyone out here is doing the same thing. It's like, I don't want to answer that because I have no idea. All right. This is so intriguing to me. The majority of the commercial CO2 that we utilize for refrigerant and other processes actually comes from the production of ethanol. So here in the Midwest, CO2 is still inexpensive, but we grow corn and soybeans here in the Midwest, where they don't on the West Coast, right? So here in the Midwest, we take bushels of corn, in particularly for producing ethanol. We do it with soy also, but bushels of corn are developed here, not for direct consumption. Like you can't eat field corn here in the Midwest. It's nasty. Sweet corn, if you grow it yourself, yeah. But commercial corn, non-edible. Here's why. We take our bushels of corn, and so a bushel is approximately 56 pounds. Now, we take that, we introduce enzymes, we introduce chemical reactions to that, and out of it, we end up with byproducts. We end up with a little bit of corn oil. So for those of you that have cooked with corn or oil and vegetable oil before, that's where it comes from. It comes from this chemical separation, this chemical process of breaking down our bushels of ground dried corn. Now remember, there's some moisture in there too. So there's oxygen in that, right? There's moisture in with this corn. We're going to get out of that distiller's grains that we use a lot for feed. So if anyone has ever seen field feed, that's actually the byproduct of our distillation to produce our ethanol. If you've ever seen that stuff, I've actually witnessed some. Had some friends that bought some for their farm to feed their animals because it was a lot cheaper than straight cracked corn, and they got wet and sit outside for a few days, and then it re-fermented, right?
Yep.
It still had a lot of yeast inside of it because yeast is one of the components that they'll use to help break this down. Here's the interesting thing. If you look at the ethanol, remember the whole process was to create ethanol. Well, that really isn't the primary process.
No.
It's a little over half. So out of that 56 pound, that bushel of corn, we actually produce about 19 pounds of ethanol, but we produce about 16 pounds of biogenetic CO2. Already filtered because of the process, because we have separated these gases completely, right? So it is a very refined CO2 gas. And that is actually one of our primary sources of CO2 that we utilize for refrigeration. Isn't that crazy?
Really, really cool.
I had no idea before we went down this rabbit hole. Like, this rabbit hole's been going on, Todd, for almost 2 years now. It's not done. There's like 90 some slides on this deck. Hopefully we'll get through 30 or 40 of them. The rest of them, you got to come to the National HVACR Education Conference to learn more about this. Okay. So let's look at this now. So we got our feedstock, our corn feedstock. It comes in, and we're going to start our fermentation process. We're going to add yeast. We're going to add different sugars, different components to it. Okay. We do end up with some ethanol, but that's not all, right? Ethanol was 19 pounds out of that 56. So the rest of it, we're going to go through more processes even. And we're going to set up a natural gas steam boiler. We're going to introduce water into it. We're going to introduce heat. And we're actually going to be capturing the byproducts off from that as CO2. And we're going to run that into an absorption system, and we're going to capture that. So we've got 2 separate forms, if not 3 separate forms of CO2 off from that ethanol production that we are going to start storing. And we're going to turn that into our refrigerant grade CO2.
Yeah, there are different grades, of course, we all know, but
Yeah.
refrigerant grade is, I think it's, correct me if I'm wrong, is 99.8 or is it 99.9? I can't remember what it is. And of course, medical grade's different, but yeah.
Right. So was any of it natural?
I don't know.
I think it seems like the only natural is what is coming out of respiration, what's coming out of the ocean, right? This is a human process to separate these. So let's step back now. And so we've looked at the natural, we've looked at the man-made versions of both methane as well as our CO2. And Dr. Silberstein, am I on the right rabbit hole here, or am I getting out of sequence too much?
It's kind of like it's almost like a hybrid.
Man.
It's not really man-made, but it's not really, yeah.
We'll talk about some synthetic ones here in a minute, which is really fun. Okay, so Todd, off from that crude oil still, we're not just going to get one gas, right?
Nope.
We're going to get quite a bit of methane because that is the simplest form, right? That is the simplest form of our hydrocarbon gas. But, okay. Whew. I feel better now.
Yeah.
It's Professor Silberstein approved, so
Yeah.
we're doing okay. All right. So off from that distillation process of our crude, we're going to end up with a variety of different highly flammable gases, A3 highly flammable gases. We're going to end up with methane. We're going to end up with ethane. So the only difference between that methane and ethane now is we're going to start bonding some of that additional carbon and hydrogen components, right? 1 carbon, 4 hydrogen, that is methane. 2 carbon, 6 hydrogen, ethane. Oh, look at that one. 3 carbon, 8 hydrogen, that's propane. We all know that one. We call that R290.
Yep.
Right? If we go to 4 carbon and 10 hydrogen, well, that's butane. Now, that's not R600A that we're quite often using.
Familiar with.
R600A is an isomer
Isomer.
called isobutane, right? But we can talk about that one later. We actually will cover that in the class. So if you want to learn more about that, how we get those isomers, you got to come to the class in the conference next week. Okay. We can go down the chain. I got 5 carbon and 12 hydrogen. That's pentane. Now, this is where it really gets intriguing. So all of you that have stayed this far, I thank you. You're nerds like us, and you want to know, all right? Because I want to know, how do we get there? How do we make these different refrigerants? Okay. Well, there's a process. It's a reaction. And we're going to start with dehydrogenation because it is the most used. Okay. It's a reaction either by chemical or by pressure or by temperature where we can change the molecular structure of a chemical. In this case, of a hydrocarbon gas.
Mm-hmm.
And there are times where we can actually introduce other reactants that help expedite that, right? Things that will cause it to work faster. And then we can by controlling temperature and controlling pressure, we can actually manipulate how we put them back together. So this is where the interesting synthetic side comes into play. And this is why I personally, so I'm not speaking for ESCO, I'm not speaking for the industry. This is personally, I personally believe that our hydrocarbons that we are using as refrigerants are synthetic gases, just like all of our previous gases. Okay. And here's why. If we start with plain old methane, Todd.
Yep. I got it right here.
Right there. Whether that thing came from a cow's either end and was collected, or it came from the ground and was collected, or it came from the crude oil distillation and was collected, wherever it came from, if I take that methane and I heat it up and I get it pretty hot, I put it in a controlled chamber and I heat it up to between 1,500 and 2,200 degrees Fahrenheit. I'm not going to ignite it. I'm warming it up. I can manipulate this thing and I can cause it to start breaking up. I can get it to start releasing hydrogen gas. Controlled. Okay. And now I've got building blocks. I can even bring in additional reactants to be able to help expedite this process. Okay.
See if I can do it without making the balloon pop.
So this particular scenario, I'm going to take methane. I'm going to introduce something like iron. There's aluminum oxide. There's a variety of different metals and some gases that I can introduce to that process that I can help it do it faster.
Correct.
So I can start drawing away some of these hydrogen components. And I can allow them to rebond with others to create new chemicals. Okay, so what we did there, we got down to the point, nope, you're good. Got down to the point where we had drawn away hydrogen gas
with iron,
bonded with one of our additional components, right? And we ended up with carbon and a couple hydrogens that naturally wants to rebond into the methane style molecule. But in this particular process, it ends up rebonding, but with another carbon, and there's not enough hydrogen components. So it ends up with a different type of bond. What is that?
Olefin. Excuse me.
That's our olefin bond. Okay, we've been talking about the olefin bond in things like R1234YF and 1233ZE, a variety of different refrigerants that use an olefin bond. And we didn't, at least I didn't, a lot of us didn't understand what that olefin bond is. That means our gas has been chemically separated and it's been brought back together.
Yes.
Okay.
But
this
guess what? But with an olefin, it's a strong bond, kind of.
Kind of. it doesn't respond the same way a standard carbon bond does. In some cases, particularly if introduced to ultraviolet radiation, it can become a very weak bond. Okay. So it's a different type of chemical, but it is still this A3 highly flammable gas. Well, we actually know this one, but we may not know that we knew this one. Any thoughts? Okay. So this one is, when we do this, we form R1150. This is one of our cryogenic, like ultra low temp refrigerant gases. It is an A3, highly flammable, has an ozone depleting potential of 0. It has a global warming potential of 3. Highly flammable, phenomenal refrigerant. Okay. It's a hydrocarbon with an olefin bond. So
Pharmaceuticals.
Pharmaceutical particular.
Yep.
Now, Todd, what would happen if we took that bond and we allowed for it to create long chains of that exact same formation?
Maybe some
What is
water.
that?
A water bottle.
Water bottle?
Plastic.
What about our polyethylenes? Why is plastic flammable? Space was a hydrocarbon.
And
It's a
if we were
chain.
and if we were to add chlorine to that, we would get something like PVC.
Exactly. So when we talk about how plastics came from oil, this is how, right? We're separating into the gases, and when we can form long enough chains, we can create structure out of those. And so polyethylene came from ethylene. It's just a longer strand of it. It's just that single carbon and 2 hydrogen with an olefin bond over and over and over and over and over. Now, let's go deeper with this, Todd. Okay. Most of us have experienced MAP gas before.
Yeah.
What is it? Well, if I rebonded in that process and I had my carbon with 2 hydrogen, and I had an individual carbon that collected into that molecule and it had that olefin bond on each side, that becomes propadiene. I'm probably saying it wrong, but
something that we know as MAP gas.
High school chemistry. That's about it. So a MAP gas is a blended gas that has methyl acetylene, propadiene, and propane. Okay. Now, if we got to the point where, Todd, we were down to a single carbon, we had used our modifiers to pull out our hydrogen gases that bonded with some of these other materials. We got down to a carbon and single hydrogen. Remember, we're doing all this with heat at this point, just heat. Well, when we rebonded, if we ended up with 2 of those, single carbon, single hydrogen, and they were attracted, we would actually get not an olefin, but a triple bond between those carbon atoms in the middle. I'm like, wow, that must be like really sophisticated. We must never see that. Well, that's acetylene.
That's what I got right here.
That's acetylene that we use in our oxygen acetylene torches.
Yeah.
It's a very volatile gas if introduced into the atmosphere, especially if the pressure changes quickly, which is why we have a desiccant inside of that acetylene bottle. That acetylene bottle, part of the reason it's so heavy is it's got a porous membrane through the entire canister.
And another reason why we keep it at a lower pressure when we have it on our regulator.
Exactly. So it's a very volatile gas in some scenarios, but that's all that it is. It's another A3 hydrocarbon that probably started with this exact same methane base, and then we just started manipulating it. And it keeps on going. Okay. R170, this is ethane. Okay. Not used very often, but it is a refrigerant. It's a highly flammable refrigerant. If we took ethane gas and we heat it up, it doesn't take as much with ethane to get it to separate. We can do this with 1300 to 1800 degrees Fahrenheit. And if we introduce water into the process, introducing hydrogen and oxygen in that entire process. So, right, steam. That's all we're doing. We're using high pressure steam. We can actually separate off those hydrogens and we can rebond back into ethylene. But when we created ethylene, Todd, we had some stragglers.
Yes, we did.
Okay. Remember, we use this high pressure steam. We separated the ethylene, but we had hydrogens and oxygens trying to find a home.
They want to bond to something.
Right. They want to bond. So in that same process,
Ethanol.
we could end up with ethanol. Doesn't have the olefin bond. They were able to bond together. They wanted to be with each other. They did, and they formed an ethanol. And this is what's really cool. Anyone ever heard of ethanol before? Okay. Ethanol is the alcohol that humans are able to consume. Now, it has an ozone depleting potential of 0. It has a ASHRAE A3 highly flammable designation to it, right? Well, Todd, how in the world can you and I, because we do sometimes, how can we as humans consume an A3 highly flammable gas?
Well, first of all, we aren't consuming pure ethanol. That's number one.
True.
Number two is hopefully we have a good functioning liver.
Okay. So, I'm telling you,
Yeah.
I'm glad you're enjoying this because this is how we feel, Aussie. I mean, this is so much fun learning about the world around us, right? Trying to keep it scientific, but scientific with crayons, the way I can understand it, because it's so intriguing to understand the world around us. Well, Todd, you mentioned that liver.
Yeah.
So let's just say we're going to put some ethanol, which could be a refrigerant, but we typically don't use ethanol as a refrigerant, but it could.
Mm-hmm.
But we prefer to consume it.
Yeah.
So I'm going to throw this question out there. You alluded to it, but let's see if anyone in the chat can help us out. What does the liver do with a hydrocarbon to make it that we can consume the thing? Another Jeopardy ticker. Okay, so step back and think about it. Think about the natural processes that we used to break apart hydrocarbons, and then think about the man-made processes that we use to break down hydrocarbons. Along that way, we can introduce things like enzymes. Okay.
Yeah.
The human body is an interesting thing. Not all animals can do it. Humans have developed an enzyme called ADH, alcohol dehydrogenase. And I'm probably saying that wrong too, but I'm getting it close. So what does it do? It does the exact same process that we were talking about earlier
with refineries. Yeah, with our refineries.
It's a refinery, Todd.
So you and I were talking about this. Is my bottle of Hennessy here, right? Yep. So here's a cool way to think about this. Whether it's something like Hennessy or Patron, your Patron bottle there, you're starting off with a mixture and using heat to separate out one of the specific molecules, that being a distillery in alcohol. Okay, so think if we all know distilleries, how it works. We're adding heat, based on how it boils. Well, we do that with the refineries too for crude oil.
Yeah.
So refineries do this, do it very similar.
Same thing.
They take the crude oil or natural gas and separate into different pieces using the temperature, as you talked about, maybe even pressure
or enzymes.
Enzymes, yes. But here's where it really gets interesting, right? So instead of stopping there, we actually take those small molecules like methane, as you talked about, where we started off with. I don't have a methane molecule, it popped, and chemically rebuild them into entirely new ones.
New stuff.
Right? So like refrigerants. right? Designed to have the exact same pressure and temperatures that we need in our regular heating, air conditioning, refrigeration.
Yeah.
So in a way, it starts with like a distillery, right? Either we're distilling the crude oil to make methane, and methane to then we take the methane product, we heat it up, we change, then of course we change it to what we need.
Hmm.
Um, but it's basically chemistry lab. So back to your
Yeah.
point. Back to your point. Is it synthetic or not?
Right.
I don't know.
Makes you think about it. Charles, you're right. So what we end up doing in that enzymatic process inside of our liver, we take those sugars that were in that alcohol. We call it alcohol. It's a blended of alcohol. It's alcohol with other components like
Correct.
sugars, right? And it separates them, and then it dehydrogenates the hydrocarbons and converts them into other simple chemicals that we can actually use. And so when we talk about how it damages the liver, it actually turns it into to acids. Oh my gosh,
Yes, Aussie. It cooks the liver.
it does. It's exactly right. Especially
That's
when
why I
we
said. That's why I said make sure you have a good functioning liver to
yeah,
consume the
right, because
ethanol.
we're just using those enzymes to break things. It breaks down all sorts of different chemicals, but alcohol, it works really hard. And when it can't break it completely, we absorb some of it into our bloodstream, and that's where some of the other side effects comes because our
Yes.
liver couldn't break it down fast enough. So, all to say that is one process. Well, we still got 10 minutes. We're ready to do another one?
Yeah. Let's add
Okay.
some.
I
Let's
hope
add some.
everyone's mind was blown. I hope everyone's going, really? Is that what we're doing? Is like all of this come
Well,
back to oil?
but see, even
Most of
so,
it.
where we're going to go next is, well, all those hydrocarbons are A3s.
Yeah.
How do we make them A2s or A1s?
Yeah.
Let's see. Show us how it's
Okay.
done.
Okay. Another reaction is called defluorination. Okay. It's another chemical reaction where we're going to remove fluorine atoms from our molecule. We can use different inhibitors, we can use enzymes, we can use different processes, but we can take a chemical and we can change it. Remember, these are all manufactured gases. So what we do, so let's just say we're going to start with this fluorocarbon. And there's ways we can get from a hydrocarbon to the fluorocarbon. It's not a big deal. We'll be doing that in our class at the conference. So let's just say we got this fluorocarbon chemical. And I heat this sucker up. Around 1800 degrees, I can start separating fluorine off. And I can use like an accelerant like our iron. Or, one of these others so that I can remove the fluorines. Now, what about chlorines? We talk about chlorines all the time. Same thing. We can separate the chlorines off from these molecules the exact same way. So chlorocarbon, right? Heat this sucker up. I can remove my chlorines and I can produce different gases. All of that to show that we really are manufacturing all of these gases. The word natural is only in reference to a chemical that is available in nature, but we're actually manufacturing most of the ones that we use.
Maybe we should retitle as synthetically natural.
Synthetically natural refrigerants. I think we should give it some consideration. I think everyone should rethink about our refrigerants and understand that, okay, so there's one of the things that I'm not going to go into any kind of conspiracy theories. I'm just going to say that oil is not going to last forever. And if we run out of oil, we run out of all of the refrigerants that we know.
And then some.
Okay. So are there ways that we can manufacture chemicals using actual natural components? And one that is taking a lot of precedent in the industry right now, I would say it's a developing technology, is using electrolysis, using electricity to convert. If we take CO2, say if we can naturally capture CO2, we can introduce it to water. So we have carbon, oxygen, hydrogen. I can actually use electrolysis to change the molecular structure to produce things like ethylene from CO2, right? I can take the bad and convert it to something that hopefully I can put in a contained sealed system and not allow it to escape. So we're looking at ways to produce new refrigerants, new chemicals, new molecules without being petroleum-based hydrocarbon molecules. That's nuts. We're not even halfway through this slide deck, Todd. That's how deep of a rabbit hole this thing has been. So in the chat, let us know what you think. There's a lot of people hanging on. There's not a lot of comments. Either everyone is going, oh, this makes sense, or they're going, what the heck did I just spend an hour listening to?
Or the other time we just bored them to tears and they fell asleep.
Yeah.
That's possible.
We want to know, because this is the kind of thing we like to do. We like to truly learn about the industry and the world that we live in. And when we understand how these refrigerants are made, it helps us understand the changes that we are going through, right?
And it's interesting because years ago when I took my EPA, you're talking CFCs, chlorofluorocarbons, and all these makeups, HCFCs, right? Hydrofluorocarbons, etc. And it didn't make sense to me at the time, many years ago.
Yeah.
You walk this like, oh, that's what that means. And be able to draw the bigger picture of where these things came from is really helpful.
Yeah.
And then, of course, why is fluorine bad? Why
Right.
is chlorine bad? Right? Then we start talking about your ODP and GWP and why we're kind of Brett Wetzel and I did it, the history of CO2, right?
Yep.
We started out with CO2 and then like, hey, guess what? We can make synthetic refrigerants, true synthetic refrigerants. And now we're coming back full circle to CO2, natural refrigerants.
Yeah. Sharp Sunny, I know this was deep. That's why I tried to forewarn everyone up front. But as you grow as a professional in this industry, now you've got a foundation. When someone says, it's just the compressor manufacturers and the refrigerant manufacturers, the patent ran out and they got to come up with something new. No, the fact is we don't have an endless supply of refrigerants. We have to be creative. And, Aussie, you're right. Now, I will be the first one to say, I have lived vegetarian for a few years of my life. I love cooked cow. I just do.
Gotta love your steak.
There would be a solution if we produced less commercial harvested meat, and we used a lot of our actual corn or a lot of our grain to produce things like CO2. Yeah, we have long-term solutions. When we look at what our long-term solutions are, hydrocarbons are not the long-term. They're probably our next phase.
I would say so. We're it's back to your bridge or A2Ls, right?
Yes.
They're that bridge to go back to the natural refrigerant.
Yep.
And that's going to be what, a couple decades, and then we're going to have to figure something else out.
2036, the HFC phase down based on the AMAC and the Kigali Amendment to the Montreal Protocol dictates an 85% reduction of all HFC refrigerants by 2036. And we are still on track for that. 2029 is when we will see, or 28 or 29, we see that next 30% reduction in the manufacturing of HFCs, which means we're just a few years away from not having enough HFC refrigerants for an industry, which means we have to go to other things. Are they going to be HFOs, which are synthetically modified HFCs? Or are we going to hydrocarbons? Or are we going to CO2? That's the big questions. You're right. There's a lot of change happening in a short window of time. One generation.
10 years. 10 years.
Yeah. Wow. That's some good stuff, Todd. All right. We hope everyone is going to be joining us at the 2026 National HVACR Education Conference. We will be out there. I'm actually heading out tomorrow night, flying out. And also, everyone joining us, we are grateful. We have another sponsor of our mobile studio and the show, Tech Source Tools. I've got them in the back. We got a logo that'll be coming for them. They will be just helping schools have the right tools and the right solutions and the right sources. And we're glad that they're hanging out with us and they're helping you grow as a professional in the industry.
Nice.
And Todd, you'll be back here in a couple of weeks.
Yeah, and I threw
Managing
the
phone.
Tech Source Tools down there on the ticker, so that way if they want to navigate
If I
there,
want to
feel
check those
take
out.
free. And it's not too late to join us at the conference.
Heck no.
You
Lots
know,
of them
it's
now. The discounted rates on the hotel I know have been gone for a little while, but there's still opportunities. And the South Point's not an expensive
not too bad.
hotel anyhow. So very
Yeah,
good. Yeah, can't wait to be there with everybody.
absolutely.
Cool. Well, Todd, thank you, sir. And everyone
Well,
come back
thank
in
you.
2 weeks. Hang out with Todd and
Yeah.
Dirk and Jocelyn and dive into, I am not even telling. And I don't know about next week's show. I'll be coming back on Thursday. Hopefully we're going to be doing a recap. But we'll see how flights and all that goes. So should see a show next week. If not, I'll prepare something for us. And then I will see you all here in a couple of weeks.
Cheers.
See you later. Everybody have a
Take
good
care.
night. And we'll see you the next time on Did You Know the ESCO HVAC show. Bye, everybody.